So we talked about static mean field games last time to the summary. It was just this morning, so we don't have to do much. But we considered, remember, homogeneous symmetric n-player games and defined associated mean field equilibria. And then we showed that under continuity assumptions on the payoff function and compactness of the state space, action space, the mean field equilibria exist. And the class of mean field equilibria is actually equal to the class of limit points of epsilon n Nash equilibrium, as the epsilon n goes to 0. Okay, so that's what we showed. But of course, there's some interesting questions about when one can compute MFEs, because remember we said one of the original motivations was the n-player games are not computable. So then we said, okay, we'll take this limit theorem. So at least there's one case where for potential games, where there's this nice paper by Mondra Shapley, 96, when you have a potential G, not necessarily concave, one can show, this is a nice little exercise, that M is an MFE, so M is something in the probability space of actions, if and only if this is the directional derivative of G is less than or equal to 0. In other words, M is an MFE if it locally maximizes the potential function, okay? And other specific algorithms you have in specific cases, but I will, put a list of references. I'm not going to be talking much about computational methods today, but I'll definitely. There are some very interesting questions there, yes. Yes, so it's a directional derivative. Yeah, and remember I was in the case where, so there's actually a way to, that's a very good question, there's a way to define, and this arises in mean field games in RD and things too, how do you define derivatives in the directional derivatives of the space of probability measures, because that's not a vector space. And so there's actually some very interesting work there, which I'll touch upon tomorrow, tomorrow, the third lecture. But here it was simple because we just said, consider finite state space. So then you identify probability measures with the simplex, and then directional derivatives are simply the same as what you would have in Euclidean space. So it's a directional derivative at a point on the simplex in another direction, which will also stay in the simplex. So there's nothing complicated about that. Thanks for asking. Okay. So, okay, fine. But remember, this was one of the motivating problems we had started with. And in the last homogeneous setting, remember here, what would be the agents, right? What would be the different agents? They would be different players who would have different source destinations, right? And their action space then would be, paths going from source to destination. But the path going from 0 to t is not the same as the set of paths going from A to B, right? So really, that's not a homogeneous setting. So there's a much more realistic framework is obtained by introducing different types of agents. And so we want to consider what happens when you have different types of agents. Okay, so now what is the setup for the n-agent model? So since you've seen the previous version, this isn't too hard, but so this goes back all the way to Mas-Colell in 1984, and there's a version of it, Blanchet and Carlier. Some economists are very interested in this kind of thing. So T is a type space now, so you have different types of agents. A is an action space, and again, I assume that T is some nice complete separable metric space. A is, as usual, a compact metric space. Then what you have is the ith agent has a type, some Ti, which belongs to T. And then it chooses an action AI. I think someone asked me this in the morning about, whether it's choosing an action, the same space for all actions, but here, no. Depending on your type, you may be constrained to the set of actions that you can choose, right? Which depends on your type, okay? So this is a map from the type space to a subset of the space of actions, okay? So it's a set-valued map, and then we assume that that is continuous as a set-valued map, which simply means that the graph of this set-value defined in this way is closed, and the set-valued map is hemi-continuous, which means this thing. Okay, so if you have a set of types that converge to another type, then there exists some action in there such that the actions will converge along some subset. Okay, so that's just some conditions, some technical conditions, which really people often call continuity of a set-valued map. Yeah. Exactly. But so what does nearby mean exactly? And that's what this says. Yeah, nearby sets in this following sense here. Yeah, okay. And then, of course, again, as before, the ith agent will choose its action so as to maximize its objective function. And the objective function looks the same, except now it also depends on the type. Okay? So now you have this probability, and look at this now, will be on the probability measures of types cross actions, and then this will be on types and actions. So this is what you get. Okay? And again, I'll assume F is assumed bounded and continuous. Okay? And so it'll be uniformly continuous because everything is in a nice space. Okay, okay. And then this is also, we know already the same thing. So now the only difference is that an epsilon Nash equilibrium with a certain type vector, so it's associated with a certain type vector, is any vector of actions such that AI belongs to CTI, so it obeys the admissibility or constraint conditions. And then you have the same thing that you had earlier. But now, of course, your function is a function of all the types as well as the actions. Okay, so everything is the same, except now you also have types and actions. And this is another way to write this in terms of the payoff functions. Okay, so you would have this for each B in CTI and I equals 1. Yeah, I'm going to, okay, thank you for a nice segue there. So in the case of congestions, you have some finite graph, so it's always these congestion games on networks, you have a finite graph. The types of agents are in fact the source and destination pairs. And the action space, CT, for each agent of some type ij is a set of Hamiltonian paths, which just means subset of the edges such that they can be reordered so you can go from the source to destination that connect I to j, right? Okay? And then the objective function will look something like this. I think I wrote this earlier. So it's the congestion over all the links in that path. Okay, and the CE can be some function that's increasing with edge congestion cost. Okay, and LE of M, so it, of course, CE is something that's increasing on the load, and the load is some function of the fraction of agents using the edge. It could be LEM, could just be M, in fact, if you want. So, okay, so it's the fraction of agents using the edge E. Is that clear? Any questions? Okay. I mean, LEM could be ME, yes.
Basic question, what's the Hamiltonian path?
Yeah, I just said it. I said that it's just some subset of edges such that, so for instance, here would be such that it can be made into a path from here to here. Yeah. So it's essentially just think paths, all sets of paths. No, doesn't. Yeah, that's why I said here I'm saying it in this sense. It's not something that goes through all, it's just Hamiltonian with respect to sort of that ij. Just has to include I and j and go through. Yeah, okay. So, right, so we have this and, okay, I think I repeated, okay. So now we can let this, I want to now, for every type, I look at this AI hat of n, sorry, this should be A hat, is some measurable function such that this is a Nash equilibrium with this type vector. Okay, so here, remember now, you want to, actually, let's go back to the congestion game to understand what we're trying to ask here. So what kind of question? So suppose, in the sense from a very practical point of view, suppose you've, over the last month or so, you've collected data on how many people have gone on how many paths, okay? Then you can think of, you have a distribution of types. You know how many, on average, what's the probability that someone wants to go like this, like this. So you have a histogram from the data that you've collected over the last month, and you can say that is going to be your sort of type distribution that you think is the typical type distribution. But the one that's actually observed on any one day, so you would think you're sampling every day from that type distribution. But on any one day, your actual source-destination pair can be very different from that type distribution. It can deviate. But you expect that on average, that's the type distribution. I mean, of course, if there's non-stationarity effects, that's a different matter. But you could account for that potentially, okay? So this is just a way of saying. So now what we're going to look at is really, with respect to random types, if you're given a type, then you have a Nash equilibrium. But now we're going to have the types being chosen from some distribution, IID, okay? So you think of them as sample. And then we're going to say, then you get this random Nash equilibrium, and you want to ask questions about how that behaves. So you might say, okay, what does that look like? Again, can we do this limiting argument? So we'll see, we'll have a similar mean field game, mean field equilibrium. It's in this context with these random types. It's called a Coulomb-Nash equilibrium. But then in addition, we want to say, okay, what's the probability that you would really deviate? So those are the kinds of questions we want to ask. So with that in mind, then I can explain why I have this function that goes from t to, they don't have to know how many other players, they just need to know the empirical distribution. So that's essentially how much load there is on the others, which potentially you could see by looking at how your red lines are on your Google map or something. Right? It's like the congestion on that day. So it's not unreasonable, yeah. So then you have, this is the random Nash equilibrium vector, okay, your AIN, which is your action, but now that's a function of your random T1N. TINs are IID samples from the lambda 0, and I thought you should think of lambda 0 as maybe something that you collected from past data, for instance. And and then you have this usual mu. Yeah, I said X hat, it should be AI. AI should be A, not X. Yeah, it's just all of these, A. Okay, so now again, we're going to assume that F is jointly continuous, but now it's on the graph of this and this, the probability of the graph, which is defined in this way. Okay, so it's just a set of measures on the joint type and action distribution such that you make sure that it's admissible, right? You don't allow anything where the action is chosen which is not admissible for the type. That's all it's saying, okay? So it's just allowing all these constraints to be taken into account. And that CT, of course, is non-empty for every type, that there is some action that everybody can choose, okay? And then C is continuous, which I told you what I mean by that already, okay? That the graph, I mean, what it means for a graph to be continuous, that means this graph C is closed and C is lower hemi-continuous in the same way. Yeah, here there are just a finite number, every finite number. Often the action space will just be finite, but there are cases when you may not. You may have it, but we want it compact in any case. Yeah, but often in this congestion games, you have finite. And for the graphs, you always have just finite space. Yeah, with the discrete. Okay. So again, now you have this random equilibrium type action distribution where the randomness is coming from the types, right? And you want to focus on the asymptotics for mu n. Okay. Again, because this is hard to analyze. And again, as before, we have this limit expressed in terms of some non-atomic game. By that means a continuum game with a continuum of agents, right? So now the corresponding mean field equilibrium, which is now called a Coulomb-Nash, is that it's of course now depends on the type. So for given a distribution of types, right, then the set of Coulomb-Nash equilibria associated with that distribution, type distribution, is the set of measures on the joint type, such that, of course, the first marginal of this must be lambda, okay? And it should give all mass on admissible types, admissible actions with respect to the type, and, it should be soup here. Okay, so in congestion, it's actually more natural to write a minimum, but I just wanted to keep it, so this should be a soup, Okay, so as before. Okay, because I put a minus sign in the payoff function. Okay, so then you can show this is not, it's similar to the, okay, I'll tell you something about the proof, but again, you look at this probability 1, that again here, I'm not saying anything about the uniqueness or anything of this. So it's a set of Coulomb-Nash equilibria. So this M lambda 0 is a set of probability measures, right, on this type distribution. So with probability 1, these are all probability measures on T cross A, right? The distance between this and this, defined in this way, right, the smallest difference away, is going to 0, where D is any metric compatible with weak convergence. Okay, is that clear? So if you're on finite space, it's just Euclidean metric, really. Okay, it's on the simplex. Pardon? Lambda 0 is where I chose my types from. For the mu n, my types are IID sampled from lambda 0. So that was my original type. This is for any lambda. This is my set, my m lambda. But my mu n was defined with lambda 0 being the TIs, IID from lambda 0. Okay, that's the connection with right? So remember, lambda 0 was what you sort of had seen as being the typical source-destination pair distribution. And then this is what you realize on that particular day, this mu n m lambda 0. Is that clear? Okay. Okay, so the proof of this goes quite similarly, like we did it out for the case without types. So it has a similar flavor, so I'm not going to go through the details, except I will say that there's one additional theorem that has to go through, that you have to actually use and invoke in order to prove it. So you should, if you want to try to prove it, you can try to use Burgess' theorem. Yeah, you have a question. This is an inf. This I mentioned should be soup. Yeah. Yeah, I said soup because, in the congestion game, it's natural to have a minimization, but then I changed the payoff, but I forgot to change this inf to soup. No. I mean, it's amazing you're awake to notice the inf soup. I'm like, I am encouraged. Yeah. No. This is the non-atomic. This is the Cournot-Nash equilibria is the same as MFE before. So we defined what the original one was, right? So we defined these were the Nash equilibrium, which we already defined for the n player. And these mu n's were some it could be any Nash equilibrium, for some choice of Ti and Ain. So it's just some measurable function such that this is a Nash equilibrium, right? So it's saying the same thing as before, but here we're saying, we can do the same thing with epsilon n Nash equilibrium, but here we can even just say if it's a Nash equilibrium, it's converging. But you can do it for epsilon n as well. I mean, you could try, but the point is that the Nash equilibrium itself so the Cournot-Nash equilibrium, that is for the non-atomic game, is already capturing everything.
You could say that, okay, even in this setting, even if Nash equilibrium does not exist, epsilon Nash equilibrium does exist. And then you can
but again, I think here it's more natural to just go to mixed. Yeah, because if they don't exist, then there's, for the n-player games, then the statement is sort of not, is void. I mean, there's nothing wrong with the theorem, but there's no real measurable function that makes sense. You're saying if it's not there for the n, but it's there for the limit.
It's not there for non-atomic.
Well, the thing is that usually here, as in under the conditions that we're saying, the existence of a Cournot-Nash equilibrium falls. Like even the MFE, we had no problem actually asking for existence of a Nash equilibrium. So of course, if you have cases when maybe your function is not continuous, and there are actually some examples, then maybe you cannot apply, like in the original, even in this you could ask even in the original homogeneous setting. So there, maybe you can't apply Kakutani's theorem because something fails. Then you might try to ask such a question. But yeah, here, remember, even in the MFE, and here too you're guaranteed. So that question is not so relevant under these assumptions, but it's not clear that whether you would, that doing an epsilon, I think it would be more natural to do the relaxed version. And then you would get, again, it would become, you are guaranteed even with the not so good conditions, and then, yeah. No, that's a little bit of Wardrop equilibrium is specific to congestion games. Yeah, and so, in a particular kind, so that's it. Okay. So anyway, you need to do something about the constraint space. I'm not going to go into detail with this, but you have this additional constraint map which causes the heterogeneity and causes, so you need to do some extra work, and you need to show something about joint continuity of F star, which is this other thing. Here I've done it properly, Prasad, soup. Okay, so then here F star is jointly continuous and this graph is closed, and so it's really new. You need conditions to apply Kakutani again. So you need to get, and other results. Okay, so like I said, the proof is similar in spirit to the convergence here in the homogeneous case, but we need to use some additional arguments, and that's left as an exercise, both the proof of this theorem and how to apply it, right? So, okay, but fine. So that's just saying that we had some things for the homogeneous case. We can do them for this heterogeneous case. I didn't talk about the converse result, etc. Okay, which means that is just fully guaranteeing all subsequential limits. The same kind of thing holds. But I want to go to something slightly different in this context, which would be interesting, which is, this is a first order result. Like it's a law of large numbers kind of result, which is saying that, if you have these Nash equilibria, I look at the empirical measure, it's converging to something in the limit. But we want to interested in finer results, like deviations of mu n from m lambda. So for instance, let's say this m lambda 0 is unique, right? So you had a unique Cournot-Nash equilibrium. And again, you can easily find conditions on all these maps, everything under which you have a unique. And there are also many interesting examples where you don't, same thing. The congestion games, if they're potential games with strictly concave, you will again get a unique Nash equilibrium, Cournot-Nash. And so anyway, we're interested in finer results and deviations of this. So how do I want to interpret it intuitively? So again, in the context of this congestion game, so what's the probability that today suddenly the congestion on certain kinds of links is going to be extremely high, even though you've sort of built your network such that on average, based on your lambda 0, everything should be working with the right kind of delays. But what would be the probability that something, that the delays are just going to be extremely large, right? Okay, so you might want to ask some question like that. And so what we want to do is sort of understand the large deviations of this mu n, this Nash equilibrium sequence from the Cournot-Nash. So large deviations is an asymptotic theory. This is for most of you, it's not needed, but that characterizes the asymptotic probability of rare events. So this is when you have a sequence of, say, random variables taking values in some space, and this probability, when it lies in A, is decaying like exponentially fast of the form e to the Sn ia, then where I is some function that goes from the space to 0 to infinity, and it has some nice regularity properties, such as lower semi-continuity, compact level sets, so that these conditions just ensure that this thing is attained, okay? So when you have this, then one says that this nu n satisfies a large deviation principle on S with some speed and this good rate function I, okay? Okay, so it's really just saying I have a bunch of probabilities and they're decaying exponentially, and I want to understand the rate at which they decay, and I want to understand the exponent as well. Okay, and this is often given in terms of some variational problem. IA and IS itself is sometimes also expressed in terms of another variation problem. So what it does is large division converts the probabilities into variational problems in some sense, and then you can maybe try to solve them just to get insight. Okay. So just a basic theorem is that if you have yi or iid on some Polish space with some common distribution theta, and you define this to be the empirical measure of these yi's, and now you define this relative entropy function, okay, which is log n of this d nu, if nu is absolutely continuous with respect to theta, in which case this is the Radon-Nikodym derivative, and otherwise it's infinity. Okay, these things really are quite simple when you're on a finite state space. You're just looking at summation, and this is just the ratio of nu I to theta I. Absolute continuity is saying that if any time theta puts 0 mass on something, so does nu. Okay, so this is really a simple expression, okay, which is just a sum on a finite state space, which is probably enough for this. Okay, then you say Sarnoff's theorem says that if you have these yiid, then this nu n satisfies a large deviation principle with this rate function, which is the relative entropy. Okay, so this is a very classical theorem that we all know. And the reason I bring this up is because we would expect some sort of relative entropy to pop up because we have this type distributions coming from a lambda I, right? And relative entropy has some nice, properties. And so it's sort of, you can do some nice minimization problems and variational problems with relative entropy. So it's nice if you think that your rate function may be expressed in terms of relative entropy. Okay, so what do we have? So now we define M. Remember, M lambda was the Cournot-Nash equilibrium associated with a type distribution lambda. And now I'm taking M to be the union over all, this should be T, of all type distributions, all possible type distributions. And I look at all possible Cournot-Nash equilibria that I could get for any type distribution. Okay, that's my M. Yeah. And remember, this was the Nash equilibrium thing. So this is the first case. So here's, before I say anything, so we're looking at sort of large deviation principles, right? But now what are we looking for? We're looking for the Nash equilibria of the n-player game, so the empirical measure of the Nash equilibrium, which could be non-unique, And we want to know how that deviates from the Kuhn-Nash equilibrium, which could also be non-unique. Okay? So we're looking for large deviation in a space of sort of subsets of probability measures. Right? So before we do something that complicated, first let's try to do it just for the case when the limit one is unique. Okay? And we take a particular sequence of Nash equilibrium. So that's what I'm doing here, the case of a unique Kuhn-Nash equilibrium. So that means that m lambda is equal to 1 for every lambda in the type distribution. Okay, so it's not just unique for the lambda 0, but it's actually unique for every version, because when you do large deviations, you'll be looking at different possible type distributions, and I'm saying it's unique for all probability distributions. Okay, which usually if it is for one lambda 0, the structure of the problem will be such that it is for many, so it's not a big restriction, but still it is. Okay, at least all of them which are absolutely continuous with respect to lambda 0, the original type distribution. Okay, then the sequence mu n satisfies a large deviation principle in the space of probability measures on type cross action with a rate function I, which has a relative entropy component. So what does it say? It looks at m, which is the first marginal of your. So remember, m is something on P cross A. So I am looking at the relative entropy of the first marginal of this type distribution with respect to the base type distribution. If this type distribution, the first marginal lies in this space M, right? It's a possible, otherwise it's infinity. Clearly, if it's not something that could arise, then it will be, that's not, where MW is equal to the T marginal of M in T. So it should not be W marginal, but T marginal, okay? No, T is this, but this is no, M here, yes. So one second, let me see. M is the set, yes, M is the set of action space. Yes, this is if the second marginal lies in M, thank you. Yeah, but it's the first marginal relative entropy with respect to this if the second marginal lies in M. Let me just see here, one second here. Lambda 0, so M lambda is the set of, let's go back to the definition so that it's all clear. So M lambda is with type is defined as a set. So here, remember, it is actually probability measures on T cross A. So it's actually the first marginal here. It's the probability measures on T cross A with first marginal equal to lambda that satisfy this. So what are you doing when you want to find the other one? You're going to do a change of measure. And you have to make sure that when you do the change of measure, that's something that could arise as a possible type distribution. So it is the first marginal, that's fine, except I should have written T instead of W. I'll change that before we post it. Yes, yeah, you're capturing that, which is in the scenario that I told you, a natural question, right? Exactly. And so you would think, okay, now I should be able to do nice infimization things with this, but in fact, this marginalization is quite, spoils a lot of the nice properties of relative entropy. So calculating this inf nu in A and I nu is actually much harder once you have this. You don't have the nice, in terms of M, remember M is a measure on PT cross A, and the first measure is something that you can have. It's all of the lambdas in P, that's M lambda. So going back to yours, right? This is the union over the M lambdas, which is all the, so you have to have the first one in this type. Okay, so it's equal to the W marginal of this M T cross A. Okay. So then, you might want to say, okay, what does that really tell you? Do you have a sort of conditional limit theorem, right? Because you want to say is that suppose I know that my today's pattern is looking like this, what can I say about the Nash equilibrium? What are the congestion points going to look like? So this is sort of telling you where, so conditioned on the fact that now I have a different distribution, I can actually say that my Nash equilibria are going to lie in this set. Okay, you might not be able to interpret this set explicitly, but this is given pretty explicitly. And this is a little, there are some closure and taking interiors and closures here, which is a little bit subtle, but I'm not going to go into those details. Okay, so this is the set of, so D is just some subset of the probability measures on type cross-action space. And this is a set of those intersection, the allowable ones that you could get from all type distributions, such that your HMW lambda is actually equal to the rate function. Okay, so it's similar to what you would expect, for instance, from Sanoff's theorem, except this marginalization makes this thing actually a little bit hard to solve, right? Whereas in Sanoff's theorem, you can get a more explicit expression from this. Okay, so anyway, this is the intuitive statement that it says, so you can actually get some information about this. Because the main randomness is coming from the first. So all the randomness is lying in the MW, and the Nash equilibrium are all functions of this lambda. So it's all hidden in the mapping that takes the type to the Nash equilibria.
So the uniqueness.
Yeah, so everything is sort of hidden in this M. Everything is hidden in the M. It's coming up, the action is coming up in the M, and which is why that makes this actually informization, this problem actually harder, but it's all hidden in the structure of M. And if you look at the structure of M condition on the types, it's not as, yeah. Okay, so if you say, okay, if you set the random equilibrium type distributions to be NN, for instance, now I'm saying without the uniqueness assumption. So there's not this mu n sequence, right? But I now want to look at NN and I want to see, so there might be, I want to say before, I don't want to go to this, so suppose I look, mu n was in this case a unique sequence, right? In both at the n level and at the limit. But now suppose I have a set of Nash equilibria and I want to see how it deviates from another set. Right? So of course we can define large deviations on any topological space, right? So let me first tell you what the statement is. First we had to sort of think how can you actually talk about large deviations converging? So of course at the law of large numbers level, you know that the distance between these two sets is going to 0. That's what we proved earlier, okay? So that we know. But so can we just use that and also get a large deviation principle? Why does a topology matter in a large deviation principle? You know, the topology with respect, so we'll explain that now. Okay, so first let me just say C is a collection of closed subsets of probability measures, okay? Because now we want to think of, okay, so I'm going to say that NN satisfies a large deviation principle. This turns out to be a closed subset of you know, probability measures in T cross A. So it satisfies an LDP in this collection of closed with a good rate function I, where this rate function is given explicitly in this form. Exactly. So I'm coming to that. And so that means this, you know, for where U is some collection of closed subsets, then this is e to the minus I n U, where this is defined. Okay. So, okay, but a more precise statement, as I've said, of course, is just for all Borel subsets, you know, this is really the precise definition of a large deviation principle, but with respect to what topology? On the set of closed subsets, right? So it turns out that the correct one is something called the upper Vietoris topology. And if you haven't heard of Vietoris before, then he is a man to have reckoned with. He wrote his last paper at the age of 103. I think he passed away at 108. And that 103 paper was well cited. So he's quite a man to reckon with, yes. So, and he came up with this topology, so which is generated by, so what is this upper Vietoris topology? There's also a lower Vietoris topology, but turns out, what is it? So I have to tell you what generates the topology. So it's this set of open sets of the form A, all sets A and C, where A is a subset of E, where E is an open subset of P2. Okay, it doesn't matter, you don't have to digest this right now, but this is an explicit topology. But if you think a little bit and you know a little bit about topology and you look at this definition, you see this is an extremely coarse topology. So you might be, when we first got this, we said, oh, okay, we can actually prove it in this topology. But does it give us any information at all? So why do you care about the topology? Let's see if I actually said this, yes. So anyway, any questions on this? Is this clear what the topology is? Maybe I'll let you digest a bit. It's not very clear, but you can think about what subsets will converge or not, but you have to sort of, you know, write it down and think about it a bit. If I say it, then, you know, we'll say, okay, yes or no, but you should really think about it to get it. Yes, class of subsets of, so remember C is the closed subsets of probability measures on T cross A.
Right.
So we have closed subsets and I want to say which closed subsets are converging to which closed subsets. right? And the base over here is generated by open sets of the form A, which is closed subsets. So the open sets in the topology, which is subsets of, probability measures, are those which are contained in an open subset of this. Okay? And if you think a little bit about this is actually a very coarse topology, which is usually not a good thing, because why do you want to do large deviation principles? So you want to do you have something called the contraction mapping principle, which implies that if you have an LDP for a sequence Nn, for instance, it also implies an LDP for the corresponding sequence f of Nn, where f is a continuous functional with respect to the topology with which you know. So if you can have a topology which has a large number of functions which are continuous with respect to it, then proving the large deviation principle has a lot of implications for many other things that you would be interested in, okay? So first we should ask, of course, the Nash equilibrium themselves, the empirical measure of the Nash equilibrium themselves are okay, are of some interest, but what is a nice quantity that people are interested in for these kind of static games, which is a functional, maybe of the Nash equilibrium empirical distribution, and is that going to be continuous with respect to this? Okay, that's the next question. So as I said, is this good enough to say anything useful? What interesting functionals of the mean field game would this LDP that we proved shed insight into? So there's something called the price of anarchy, so which I will define to you now, and that's something you want to understand. Okay, so what is the price? So in Nash equilibrium, what do you have? You have distributed, distributed decision making, right? So each person is independently making a decision as to whether or not to go by this route or that route. You could think, now instead I have a central planner who looks at everyone and sort of tells everybody exactly what to do, what routes to take, right? And everyone just follows that. So that would require certain kind of coordination, but that can only do better in terms of optimizing things than the Nash equilibrium can. So one question you want to know is, you're sort of thinking of you allowing each one to make individual decisions as being anarchic, right? And you want to know what is the price of the anarchy, which means sort of the ratio of the social optimum to the optimum of the Nash equilibrium. So that's the idea, and let me just define it explicitly. So again, I said of all admissible, I still have to have only admissible. I can't take somebody who wants to go from, San Francisco to New York. I can't take them to some Portland. So here, this still has to be maintained. But otherwise, it's all action type distributions, right? But then it's just subject to the constraint. And then the average cost for any fixed type action distribution is simply this, right? So given any type action distribution, what is the cost of that particular type action? It's just the integral of your payoff function with respect to that type action distribution. Is that clear? Okay. So then the price of anarchy of the n-player games is simply the ratio of the worst case Nash equilibrium. It's something. So I hope, because I was doing soups and so I hope I haven't. Okay, but I think the soup, of all measures of VM, that's good, to the cost, the socially optimal cost. Okay? So actually, I think this is done with the infamization in mind. Okay, so we'll have to sort of change it for, okay, this is suddenly we're doing infamizations instead of supremum. I'll change it to the, okay? So assume that we're doing infamizations and not maximizations. Okay, so then if lambda is again t, this should be t, that lambda is a probability measure on type distributions, and you set this. Again, remember A lambda is in the set of all. You can just do the corresponding thing for the limit Kuhn-Nash equilibrium game. So you just have this same ratio. Okay, again, it's looking as if you're infamizing rather than maximizing. Okay, okay. So now you have this. And so we're able to say something about the price of anarchy. So what we're able to say that if you look at R, what is R? It is in this case, it's the worst price of anarchy over all possible types that you could get. Okay? So you look at the worst case. Then for every epsilon greater than 0, there exists for all large enough n that if you choose that type distribution, your price of anarchy, the probability that it will be greater than this worst case is going to go exponentially small. Okay? Is the statement clear before the implications? Yes, it depends on epsilon. For every epsilon and c, there exists n, which depends on epsilon c, of course, such that for all n greater than n, this is this. But you can choose epsilon however small, and you're going to have an exponential decay rate. Yeah, somehow you can't just do lambda 0, right? So you have to take sort of the worst type distribution. That's the best we can say. You would expect exactly the more natural thing. Okay, if I have my current type distribution, can I say something about that? But that's not what you can say. You can say this is a true. But here's something that you have to actually keep in mind, which the reason is because you're doing the change of measure. Yeah.
But not. So this
It's not.
is not
No, the soup is not so much. Not so much. Yeah. Yeah. Okay, but let's look at what are the implications for this. So people in computer science who are interested in algorithmic game theory have studied congestion games, not large deviations questions, but actual congestion games. And they have come up with, bounds on the price of anarchy. So for instance, in the congestion game, if remember the CE was the load, was sort of a function of the load on each link. Suppose that's linear for each epsilon. So it's just some constant times the load on that link. And that load was a function of the fraction of people using that link, okay? Then they showed that for any lambda in the type distribution, all the W's are T's here. So the price of anarchy is less than equal to 4/3. Okay, but this is a worst case over all cost distributions. So what they're saying is that if I have this for any lambda, and Peter Roughgarden and Eva Torders, Tim Roughgarden showed in 2002 that if you have this, then the worst over all possible linear cost functions, so they're not fixing a cost function saying what happened, but worst case analysis overall would be less than equal to 4/3. This is for the Kuno-Nash game, right? There's no n here. So it's less than 4/3. But Katsoupias and Papadimitriou in 1999 had shown that for the n-player game, again, this should be, the type distributions, T, should be less than 5/2 for all n and all possible types. And that this is sharp in the following sense, that you could actually, for every n, you can find a certain CE, collections of CEs, such that you can achieve the 5/2. So for different n's, it could be different CEs, but you can achieve the 5/2. So which is larger, right, than 4/3, even though it's the afternoon, that much I'm able to keep track of. So it's 5/2 and it's 4/3. So, but this says that actually you can't do, so this is really the worst R, in some sense, it's saying 4/3. But here you're saying our result shows you that actually this will not be greater than 4/3. So for it to be greater than 4/3, it's with exponentially small probability. So the point is that they're doing a worst case scenario, and then they're saying it could be as large as 5/2, but we're saying this is sort of a more natural thing, that the limit problem is actually capturing what can go on in the end. It's just with really, really decreasingly exponentially small probability, you'll get high congestion, but otherwise you're not going to really do that badly. No, this is tight for every n. For every n, you can find a bunch of CEs. Now there are two differences between our result and this. Theirs is all worst case. So they cannot say anything for a given CE, whereas ours is about a fixed CE, right? So we can say for a fixed CE, the probability that you're going to exceed this R can depend on the CE for us. But it's also a worst case thing, because if you look at it's not just the CEs changing, which is the issue, which is causing this to be larger. It's really the probability, it's the fact that they're doing a worst case analysis. But they're doing a worst case analysis also over all possible linear problems. And of course ours, this was restricted to linear CEs. Ours is not restricted to any linear CEs or anything, but this is sort of something that tells you that the large deviations captures really in what sense that because this suggests that maybe this limit problem is not telling you enough about the n-player problem. Because you're saying the price of anarchy in the n-player game can be much larger than the limit game. But we're saying the probability of that is really, really low. Okay? And of course, one has to see, is this just because they're taking worst case over all CEs, or whether it's this, but it's actually, I think, the fact that they're doing worst case. Possibly because this is also worst case over all CE linears.
Okay.
Yeah. this, we are also taking a soup over lambdas. I mean, not all lambdas, but all lambdas absolutely continues with lambda 0. So we are taking that soup, but it's for a fixed C, whereas this is over all C. So there could be that there's some C for which it could be lower. Exactly. Yeah. Okay. Okay. Yeah. So that's so that was at least one. First, we thought upper Vietors was fun to find out about the topology, and then much later, I found out about him, which was quite remarkable. But then the bounds, so that we could actually get something from such a from such a result, that for a meaningful functional for games was sort of, it is of that flavor, but it's a little more complicated just because of the Vietoris topology. So it's not completely just a continuous function, but it's you have to do a little more, and you know, because you can just use the closed, like you don't here, remember, no, we haven't written it as an LDP for this.
Right.
We've just written it as a bound. So you only have it for the one side. Yeah. So it's not a direct application of but thanks for the question, actually. There was a subtlety there. So yeah, I mean, we didn't try because really we wanted to get this result, but it is hard to deduce that directly from using the upper Vietoris. It could be that it's still true, but we didn't. Really, what you are interested in the Price of Anarchy is its upper deviation in some sense. So we didn't, but we did also do some other functionals that we thought are more interesting, related to another class of games, which I didn't want to get into, which are called some entry games, not congestion games, which have a different flavor. And they have a somewhat, a cost function that has a different structure. So this is a paper that was accepted a year and a half ago or something. It's supposed to appear at some point at MOR, but it's online on the MOR. So you can look at the other applications. Yeah. Okay. So that's what I wanted to say about these static games. And then the next lecture, I will talk about some mean field games in the diffusion context and sort of what you can say over there, and up there give you an outline of what is known and what's not in terms of, there are many, many more open questions. So interestingly, when we first looked at mean field games in the dynamic setting, so diffusion, of course you could do it in a discrete dynamic setting, but diffusions are sort of more natural. If you look at that, then there also you have non-uniqueness, and we thought, oh, the unique case must be really simple, and the non-unique is really quite challenging there. Then we realized there that even in the unique case, it was far from simple. So I'll try to tell you what makes it that difficult and what some of the implications are in that case and some of the open problems. So here also there are many open problems that you might have other functionals you want to look at. There are also some classes of games that we came up with Fs, which are not necessarily continuous. And can you still prove something like this in that context, which are of interest in some economic contexts. So there's a lot of open questions. You can look at our paper for that.
Convenience?
Yeah, no, I mean, the others don't work. It doesn't satisfy with respect to the Hausdorff. It doesn't satisfy with respect to something else. So
you already know that it's impossible. It's an impossible.
I am not sure. I'm sure there are many topologies on closed sets, but I'm not sure I've exhausted all of them. No. But the natural ones we tried, and I don't think that they work. They're too fine to work, but Exactly. No, so there are two things. Once we actually started, it was not that we did the Price of Anarchy first. We first said we want to find as fine a topology as possible, right? So you try to get a finer topology. It wasn't that easy to prove it because you don't get the right, bounds. So then we said, okay, let's find some. Then we found it. Oh, okay, it works with this. Then we said, is this of any use? Is this too coarse? But it wasn't. So it was. So it could be that maybe and then we said, are there other compelling functionals? So we looked at some other like entry games and said, oh, that function, does it work for that too? And it did. So if there is a compelling other functional, then one could try to, but the one thing we wanted to do is actually convince ourselves that in the non-unique case, which is quite common, reasonably common, I mean, there are a lot of places where you have uniqueness and you're interested, but there's also a lot of places where you don't have uniqueness. So we want to know whether fundamentally you would even expect a large deviation principle in that setting. And so we were like, okay, at least in static games, you know that you can get large deviation principles. So maybe you can also do this in the dynamic setting, but that's an open problem that hasn't been solved yet. Yeah, so we just said, let's do the static problem as the easier case, but then in the end, there was quite challenging here as well.
Yeah.
Yeah.